Okay. Think I'm recording now. You know what? Hold on. Yes, I'm recording. All right. So we're recording this, so if anybody needs to, they can hopefully refer to it later. All right. So today, let's look really quickly at our schedule. So got our schedule here. We're kind of wrapping up. Only a couple weeks left here. We've got a few more papers to go through, and then we'll probably swing into final presentations. I will be sending out some sort of sign-up sheet for presentations. I'll probably just be like a Google spreadsheet or something, as long as you all promise not to delete other people's names from the slots that they got that you want and replace it with your own. That's uncool. But I will send out a spreadsheet that you all can sign up for with final presentations, and we'll try to do it using Zoom, just like this. So, and I think it'd be really interesting to just hear about some of the cool things that you've been doing and some of the cool results that you've gotten. I know I really enjoy reading about your projects, and I think it would be great for the other students to hear about your projects as well. Okay, so hopefully you all turned in project 2. Remember that the final project is due kind of right at the end. I've made it due as late as possible, so it will be oh, hello, go away. It'll be due the same time as the final exam. So the final project is due on Wednesday, April 22nd. And that's all I really want to say about that. There was some question about, could the final project be worth less than 30 hours? And I think the answer is no. So I understand that things are a little bit crazy, but I mean, even if you started now on your final project, that would only be, I mean, you have all of this week, you have all of next week, you have all the week after, you have all the week after, and you have whatever time you would have spent studying for the final. So, and there's no other requirements in this class. So I think at this point, the answer is no. I'd like to keep the final project requirement at 30 hours. Now, so Cody asked a question, if you don't have anything done for presentations, you just present what you have. Yeah, so the question is, yeah, so what if you're not ready? If you're not ready, then probably what I would just say is present one of your other projects. And I think that would be okay. I'd much rather have you present your final project. And maybe what I'll do is try to figure out some way to incentivize people to present early. I know that not everybody will be able to, just depending on how much you've gotten done. I know a few of you have tried to work on your final presentations, your final projects, like as your second project or your first project. And if that's the case, then maybe you guys can be the ones that present first. We'll try to figure all that out, and I will try to push things as far back as possible. Michael asks, are we planning on using the 3 hours set aside for the final exam for presentations? I hadn't intended to. My sense is, I'd rather use class time for that. I mean, I don't know how you guys feel about it. Are there strong feelings one way or the other? I thought you guys would actually just like it if we didn't have to show up on that Wednesday. That was just my sense, though. I mean, maybe you would like to show up. I mean, virtually. It does sound nice. Yeah, yeah, it does sound nice, right? Okay, so let's go ahead and, oh, Michael says it probably depend on how early I'd have to present otherwise. Yeah. Well, tell you what, I'll try to send out the sign-up sheet as soon as I can. In fact, I'll try to do that right after class. I'm gonna just make a note to myself here. And I'll just see how people are, like, you all could sign up as soon as possible and let me know. And what I'll do, so here's what I'll do. I'll create a sign-up sheet. The sign-up sheet will have the days that we've picked for final presentations, and I'll try to figure out about how many presentations I think they're gonna be and about how much time I wanna spend on it, and I'll divide it all up by the, like, we'll probably give everybody 10 minutes or something like that to present. So I'll figure all that out, And then what I'll do is I'll create a little spreadsheet. People can sign up for different slots. And I'll also let people sign up in the final exam slot. And what that will tell me is that will tell me, given the available slots, would you rather present during the final exam, or would you rather present in one of the available slots, right? So that'll be sort of your way of voting which way you'd like to go. And then what I'll do is I'll just sort of look at that. I'll decide whether or not we're going to do presentations during the final exam time. And if we're not going to, then I'll figure out, I'll talk to all the people that wanted to present during the final exam time because they didn't want to present earlier than whatever slot was the latest available. So hopefully that makes sense. I think that'll work. I think it'll work. If that sounds too crazy to anybody, let me know. But I think it'll work. So I'll send out a little sign-up sheet, and that'll give us more information. Okay, so just looking ahead a little bit. Today we're doing FixMatch, so more semi-supervised, unsupervised learning. Next week, or sorry, Friday, we're going to be doing this paper which has had a lot of impact, a lot of chatter about it, training with CPUs. So normally we think of training and deep learning, and we all think, oh, you got to have a GPU. And these guys say, no. There are different kinds of training algorithms that map better to CPUs, and you can still get state-of-the-art performance even with a CPU. So super interesting paper. And then we'll go on just going to cover sort of some miscellaneous papers that I thought were interesting, but that hopefully will be illustrative and useful too. Send spreadsheet, myself a note. All right, so let's dive into today's paper. I just learned, by the way, last night about this pretty cool Zoom feature called breakout rooms, where we can have a chat like this, and I can actually create breakout rooms, and then I can actually farm you all out into the breakout rooms. So actually what I'm going to do for the remainder of our papers, whenever possible, I really kind of liked the rhythm that we had where you would all discuss papers and try to discuss interesting things with each other. Me just talking feels like a bit of a drag sometimes. Hopefully you like it. But I really valued the peer instruction part of our class. And so I'd like to somehow recreate that virtually. So we might try the breakouts on Friday, but I'm not ready to try them yet today. Okay, so FixMatch. The idea is semi-supervised learning. And we've just got and they sort of point this out in the paper, this is a combination of existing ideas, but I felt like it was pretty good combination. They seemed to get good results, and it was pretty straightforward. Like I felt like this paper was pretty easy to understand and pointed out a lot of really good related work and took us through some really basic but good semi-supervised ideas. So I learned a lot reading this paper, and I hope that you did too. Oh, actually, let me launch our poll about this. I'm curious. Okay, polling everybody. While I'm talking, take a few seconds and tell us how you felt about this paper. Okay, so let's go ahead and dive in. So the goal here is some sort of image classifier. And we want to build the image classifier using semi-supervised learning, which means we've got a big pile of unlabeled data and we've got a small pile of labeled data. And we'd like to somehow use the statistical information use the statistical information that we've got in the big pile to somehow help us understand just the domain that we're working with, in this case, natural images. And based on that, we want to then train a very simple classifier with just a few labels. So looks like we've only got less than half of you voting on our little poll. Please take a second and fill that out if you would. So let's go ahead and look at kind of the pipeline here. So the big idea, I think, is pretty well captured here by figure 1. So remember that we've been going through this series of ideas about self-supervised and unsupervised learning. And a lot of them have, somewhere at their heart, the idea of auxiliary tasks that are interesting, that we hope, if then we ask the neural net to solve, will convince the neural net to like understand the structure of images. And so these guys combine two ideas together. And importantly, they say like the two ideas, like you need both of them. But the two ideas are consistency regularization and pseudo labeling. So let's see if we can understand what those are. So the idea behind pseudo labeling, oh, okay, looks like, well, 52% of you have voted, 9 of you have not voted. You're all sinners. Okay, so feels like people sort of felt like this was a good paper, but not excellent. I agree with that. I think it was a good paper, like it's fine. But I didn't read it and feel like, oh my goodness, this is the best paper I've ever read. Somebody didn't like it. Okay, so let's take a look at what's going on here. So the idea is we start off with some sort of unlabeled example, horse, and we have two different augmentation functions, a weak augmenter and a strong augmenter. The weak augmenter maybe like rotates things or flips it or shrinks it, scales it, crops it, maybe does some color stuff, but the point is like it doesn't change the image too much, but it does change it a little bit. We take the weakly augmented image, we put it through our model, and the model makes some prediction. Based on that prediction, if the prediction crosses a certain threshold, so that's represented by this dashed line here, then we convert the prediction to a one-hot label. This is called a pseudo label. It's not a true label, it's just whatever label the model assigned to this image. But we treat it as if it was a true label, and we use it as part of our loss function. We then take the unlabeled example and we put it through a strong augmenter. So the strong augmenter, you can kind of see here schematically, also manipulates the image, but does it in a much more, like a much crazier way. Pass it through a model, you get some sort of prediction, and then you put this, this is called the consistency regularization term. So there's a cross entropy between the pseudo label and the model prediction. We want the labels coming out of the strongly augmented image to match the pseudo labels coming out of the weakly augmented image. So let's take a look at the details of these two cost functions. I think this paper does a pretty good job of being clean with their notation. Seth has raised his hand. So, by the way, you guys should all just feel free, if I don't notice that you've raised your hand, please feel free to just like unmute and ask a question. Totally fine. Seth, what's up?
So I was curious when reading this, like why do we even bother with weekly augmenting if all that is used for is creating the pseudo label? Like why not just run that on the original image and generate a pseudo label and then do all the training stuff?
Yeah, it looked like, so it looked like they, let's see, so as I recall, they said something about that in their ablations. It looked like they said that, where did they say this? It was at the end. Oh man, Seth, they addressed this in the paper.
Oh, okay. Yeah. I mean,
I remember.
if it's just I overlooked it, then
Well,
no worries.
they said it's in the discussion, maybe. Oh, maybe it was in the ablations. Shoot, I can't remember where they said it. And I also can't remember what exactly they said, but I swear they said something about this.
Yeah, no worries. I'll just take a closer look.
Okay, yeah, if anybody notices this while we're going through, please let me know, because it felt like the reason was they said something like you have to use you can't use the strong augmenter because it's too crazy. So you have to use the weak augmenter at least at first.
I think that's at the end of 5.2.
And 5.2, let's check. Augmentation strategy. Um, Okay, yeah, thank you, whoever pointed that out. Let's see. We also studied different combinations of weak and strong augmentations for pseudo-label generation and prediction. When we replaced the weak augmentation for label guessing with strong augmentation, we found that the model diverged early in training. This suggests that the pseudo-label needs to be generated using weakly augmented data. Using weak augmentation in place of strong augmentation to generate the model's prediction for training peaked at 45% accuracy, but was not stable and progressively collapsed to 12, suggesting the importance of strong data augmentation for model prediction at training. This observation is well aligned with those from supervised learning. So that answers maybe part of the question, which is why not just use the strong labeler, the strong augmenter, but it doesn't answer the question of why do we need an augmenter at all, the weak augmenter. And I don't know the answer to that. Let's see if we find it as we go through. It's a good question though. It's the right question. I'm glad you asked that. Okay, so let's go through, let's just go through the notation really quickly, just so that we understand exactly what's going on here. So we've got L classes, we've got a set X of labeled examples. So B is, they called it a batch. So we've got the XB and PB, P is the class, X is the image. And then we've got the unsupervised labels, which is calligraphic U, which is a set of all UB, where these indices go from 1 to mu times capital B. So they introduced this mu thing, which is a hyperparameter which controls the ratio of the labeled data to the unlabeled data. Okay, P of my given X, that's our model. So this is the neural net. You give me an image, I give you a class. And H is our cross entropy. The other thing to note is that the two augmentation functions are capital A and alpha. And that's important. So let's start with the consistency regularization thing. So consistency regularization, let's look at equation number 1 here. At first, I was weirded out by equation number 1 because I was like, hey, wait a second, why isn't this always 0? So what do you guys think? Why isn't this always 0? Right? Because I mean, notice it's the same, right? This term is the same as this term.
Is the alpha stochastic?
Alpha stochastic, yes. So because alpha is stochastic, calling it twice doesn't give you the same answer. And that's why. So yes, otherwise this is, the first term and the second term are identical. But here what you're saying is we're saying, you give me some unlabeled image, I'm going to weakly augment that labeled image. I'm going to feed that into my model. That's going to give me some logits about what class I think it is. And then I'm going to compare the logits from the first time I augment it to the second time I augment it. And what should happen is I want that norm to be minimized. So basically I want these two, I want it to be the same. So basically I want my model to be insensitive to the space of transformations captured by the weak augmenter. And we hope that the space of transformations captured by the weak augmenter is going to be something that'll tell us something about structure in the domain of natural images. Okay, so that's one of the terms. That's a consistency regularization term that we'll see. The other one is the pseudo-labeling term. So this is also just a cross-entropy term. So the idea here is you give me some sort of unlabeled, you give me some sort of unlabeled image, UB. I'm going to plug that into my model. I'm going to get some sort of distribution back out. And I'm going to go ahead and calculate Q hat B. So this is an approximate label for the Beef image. And I want to make sure that as long as, this is that thresholding term, as long as we're above the threshold, I want to minimize the, let's see, where does it give us? So Q hat B is the pseudo label and QB is just the thing that I got out of the model. So I want to sort of, so what this is going to do is this is going to push the model towards giving me things that are more confident and deterministic. So I'm going to take whatever the model gave me and I'm going to push it towards a one-hot distribution. So then the algorithm, if we look at there's two terms, and really this whole paper is about these two loss functions. Well, the whole idea of the paper is let's carefully craft these loss functions to do unsupervised learning. And so if we look at the first loss term, let's see if we can unpack this. So we've got the supervised loss. So the supervised loss is applied only to the labeled data. So here we're trying to minimize the cross entropy between PB, which is the true one-hot distribution of the Beef image, and PM, which is the distribution of predicted classes from our model under weak augmentation. So we're going to weakly augment all of the labeled images and try to make them equal to their known labels. That gives us the L sub S, the supervised loss term. So then for the unlabeled images, first we're going to get an artificial label. So that's this QB thing, given a weak augmentation. Then we're going to do cross entropy, but the cross entropy is going to be the cross entropy between the model's output on a strongly augmented image and the pseudo label obtained with a weakly augmented version of the thing. And again, we're summing here over all of the unlabeled images. And then this is the thresholding term that just tells us whether or not we're even going to include this term in our loss function. As soon as predictions become confident enough for us to trust the pseudo labels, then we'll include that term in the overall loss function. Then the final loss is just that. So we're just going to take the supervised loss and we're going to add it to the unsupervised loss, and there's some hyperparameter that just governs the trade-off between the two. And that's it. So this is really, like, to me, this was really easy. I was like, wow, this is pretty straightforward. I mean, this is such a simple loss function. Like, they're not doing anything fancy on the architecture side. Seems pretty cool. Now, the augmenters, though, I mean, there's a little bit of magic that's happening in the augmenters. So the weakly augmented images, these are like pretty straightforward. You know, you flip things, maybe you says like, you know, they translate things a little bit, etc. Strong augmentation, though, they have much stronger possibilities, and they had these two things which they got from the literature: rand augment and CTA augment. I don't really understand the details of those, but they just had like this collection of transformations, so different kinds of things that you could do. So I think like this horse that we saw had both some rotation and maybe some shearing and some color inversion. Like, it had a bunch of stuff. I mean, this was a pretty, like, that's a pretty messed up horse. I mean, I don't even know quite how they got that from that, but you know, you and I look at that, and I think we could identify that as a horse. So kind of interesting that our visual systems are so adept at being robust to these kinds of transformations. Okay. So question is, oh, and then the final thing, which they don't show, is simple weight decay regularization. So that should have been in their original loss function, but for whatever reason, they didn't put it in their loss function. They should have, though, because it's part of their loss function. So, and they sort of make this point while they're going through this little section of additional important factors. They sort of make this point that, you know, a lot of times when people are doing semi-supervised learning, they have some interesting loss function or maybe some interesting architecture, but they don't talk about some of the other parts of training, like which optimizer did you use, and what training schedule did you use, like what learning rate schedule did you use. So they sort of say, in this work, we're going to try to also account for all of that stuff. And who can tell me, well, I mean, actually it's right here, too bad. It was kind of an interesting paper because this was one of those papers where Adam wasn't the best optimizer. And in fact, not only was, well, yeah, they just said, you know, standard SGD worked much better with basic momentum. It's not often that you read papers like this, but it's just a good reminder to everybody that Adam is not, as much as we love Adam, Adam is not always the best optimizer, as hard as it is for me to say that. I really like Adam. Okay, and then they say it doesn't really seem to matter which kind of momentum you use, but they do use a cosine learning rate decay. So as far as I could tell, what this did was they said, well, actually they say it right here, it decays the learning rate from eta to pretty close to 0 following a cosine curve. So I'm sort of imagining that it starts off kind of flat and then goes down pretty fast towards the end, and then maybe flattens out a little bit at the very end. Okay, so I thought that was interesting. Let's talk about results. So the thing that amazed me about this paper, besides just being, I thought, a really nice combination of ideas, was the performance in the low label setting. So, and they sort of point that out. They say, look, we're running experiments where we only have 10 and at one point they had 1 example per class, which I thought was amazing. Like that to me is pretty awesome. It's pretty awesome that you get non-zero results when you do that. But let's go through some of these results. So I think we have some tables here. Let's start with this. So here we got CIFR 10. And this was a pretty nice paper. Like they took the time to re-implement everything in their own code base. They said they felt like that was important just to make sure that everything was like super comparable, as opposed to just like reporting numbers that you scrape out of someone else's paper that's been published. So let's take a look at some of these results. So we're looking at error rates. Here's the CIFR 10 data set. Across the top, we see the total number of labels. Remember, there's 10 classes. So in the most data-rich case, we've got 400 labels per class. But in the least data-rich case, we've only got 4 labels per class, which is like not a lot of labels. And here are the 2 different variants of their algorithm, FixMatch RA and FixMatch CTA. Remember, these are the different augmentation strategies for the strong augmenter. This is RAND augment, this is CT augment. And what's amazing to me, so first of all, error bars everywhere. Very nice, love error bars, good job. But what was amazing to me was just the fact that you got like non-zero error. I mean, with CIFR 10, you know, your error rate, if you were randomly guessing, should be 90%, right? Because you're going to guess 1 in 10 correctly. And they're getting 11% error rates, which means they're getting 9 out of 10 right, only having seen 40 labels. To me, that's really pretty cool. And I wish I understood like deeply why this is so powerful. But I mean, this isn't quite state of the art. Like you're not doing as well as you could do if you had full supervision. I think full supervision on Cipher 10, it's closer to like 98 or 99% or something. So you're still kind of far away from full accuracy. But this is really, I think, a pretty amazing number. And I think it all has to do, like you sort of, like there's some details here, like, oh, we use SGD, oh, we use weight to KO, we use cosine learning rate, blah, blah, blah. All that stuff is standard. To me, it's all about these augmentations. Like I think something about the augmentations are making this just incredibly powerful. And actually, this leads me to maybe a big idea that I just want to throw out there for everybody. You know, there's a big difference between all of the neural nets we've ever seen and what happens to a human as their visual system is trained in the early years of their life. And the big difference is time and space. So all of these sorts of batch-based image processing sorts of deep neural net algorithms, they're all based on just sets of data sets, like a bunch of static images. But in the real world, a baby is born and they're like looking around, and what they see is they see an object or a face or person or whatever it is, and they see the same thing for several, like many frames. So if a baby, for example, is looking at her mother's face, then maybe you're like staring at the face and you see it for 30 seconds. And so at 20 frames per second, that's maybe 1,000 data points. And from slightly different angles or slightly different lighting conditions as you're moved around. And so the fact that you are seeing a sequence of the same thing from slightly different perspectives or slightly different lighting or whatever it is, to me almost feels like augmentation, but augmentation in the best possible way. It's augmentation that is respective of geometry. So remember, like we've sort of pointed out that people have noticed that deep neural nets sometimes seem to operate more on texture than on shape. And my sense is all of these image augmentation things are sort of trying to remove texture from the equation and just put shape back in. But I'm thinking, if we had a stronger sense of three-dimensionality, if we had a stronger sense of depth, for example, or a stronger sense of how an object changes in response to lighting as the object is rotated, they would almost serve the same purpose as augmentations, except that they would tell us something about geometry. And I just can't help but think, wow, I wonder if we trained deep neural nets using data sets like that, if we would have data sets that were more attuned to shape as opposed to texture, just natively. And so that got me thinking, wow, I would love, like if anybody ever needs a vision project, I think it would be really cool to try to build a data set where you have some of these augmentation, like even a synthetic data set, like get a bunch of 3D objects from some 3D object database and render them, but render them with different lighting conditions or different shadows or from different angles or something like that. call that your augmentation, train a neural net, and just see if it has the same property of caring about textures more than shapes. Anyway, so to me, like that's what's really interesting about this. I am intrigued by what it is about these augmentations that make this work so well. The fact they're using pseudo labeling and consistency regularization, like, I don't know. To me, yeah, details, like that doesn't seem to be the critical thing. Okay, I'm so sorry for that detour. Let's go back and continue looking at our results. So the other results that we're noticing is, of course, as you get more labels, your performance gets better. So in every case, all of these competing algorithms are able to take advantage of more labels. So is FixMatch. And of course, when you have the most labels, you get the lowest possible errors, down in the 4% over here. But notice that it's consistent, that FixMatch is pretty much better than everybody. Although I guess the error bars here were high enough that they actually overlap with this. That's why they're both bolded. This seems to be an outlier. Like, I don't know what was going on here, because here the error bars were really quite small, and then here the error bars got bigger again. So, I mean, I don't know. I don't know what to make of their error bars. Like, error bars seem a little funny. I would expect the error bars here to be smaller than the error bars here, and these error bars just seem outlandish. But anyway, so Cipher 10 getting awesome results. Cipher 100, it's a much harder problem, and they don't do as well. And you know, I think they did some spin in their results discussion. I forget how they said it, but they said, "Oh, we're better than the state of the art in most cases, but on Cipher 100 we're competitive," or something like that. You know, like, whenever someone says they're competitive, that means someone else did better. And then the Street View house numbers data set, they were also doing pretty well. Often they were tied for first place. So pretty consistently good results compared to, they did a pretty good job of comparing against a bunch of other algorithms. And they did really, I think, really well in this particularly interesting regime of not having very many labels. Okay, so we've got a few minutes left. I wanted to turn to this section 4.4, barely supervised learning. So like, to me, this was incredible. One example per class, which is pretty awesome. So here's, for example, this one. So you give me, you do your unsupervised learning, and we're only going to give you 10 labeled images. And these are the 10 labeled images I'm going to give you. I'm pretty sure that's the boat class. And I don't know about you, but like, yeah, I guess that's an oil tanker. And I guess that's the sky, and that's the water, and there's like a very subtle line between them. But like, holy cow, that is a terrible exemplar for the boat class. So I'm amazed that it got anything at all. But they sort of point out that if you're gonna just do one example per class, the example that you give makes a really big difference. And I love this thinking. I was like, oh yeah, this is cool. Like when you get to the really low image regime, you can start asking questions like this, which I think are super cool. So they said, we think that we noticed that as we trained the model different times, we'd get different results based on which prototypes we selected. That led us to this interesting question about are images, some images, like, are they more or less prototypical? And can we pick the most prototypical images for different classes? And so they sort them, and what they said was, they said this, they said, using the same hyperparameters, the model trained only on the most prototypical examples reaches a median of 78% accuracy, maximum is 84. Training on the middle gets 65% accuracy, and training on only the outliers fails to converge completely with 10% accuracy. So what this says is, it says if you're only going to have 10 labeled images, pick carefully, because if you pick the right 10, you'll get like maximum 84% accuracy. If you pick the wrong 10, you're going to get like 10% accuracy. Now, of course, it's hard to know beforehand which are the most prototypical images, but so it's like you have to have a classifier to know that. And so they were sort of pointing out, like, look, this is not Like we understand this is not a, like you can't take advantage of this fact if you don't have something that's already trained. But I was thinking about that more and thinking, oh, I bet someone, a creative grad student, could come up with some interesting way to get prototypical images from something, some other source, maybe humans, maybe Google. I don't know, but it felt like it just felt like this is interesting to me. It's interesting that different images convey more or less prototype information about a class. Okay. Finally, they do a couple of ablations, and I mean, the results are pretty straightforward. I mean, I don't think we really need to go through these terribly carefully. Temperature matters, ratio matters, confidence threshold matters. One thing they point out was like weight decay mattered a lot. This is a pretty beautiful U plot. So remember, weight decay is just, we just strap like an L1 or an L2 norm penalty on the weights of the neural net. And this is showing like it matters quite a bit. I mean, you look at the error rate here. If you pick a number for your weight decay that's too big, say 1e negative 2, you're gonna like quadruple your error as if you just picked like 1e negative or 2e negative 4. Sorry, that's 5e negative 3 or 9e negative 3. So like it matters a lot. So this kind of hyperparameter tuning, I think, unfortunately, is just the reality of these models and algorithms. It's really too bad because it's such a pain to do. Yeah, exceptionally important. Yeah, so, all right, I think that's all I wanted to say about this paper. Any comments from the audience? What do you guys think? Anything that struck out to you? Brandon says, I like it because it feels more natural. Yeah, it feels like kind of a straightforward idea that just kind of works. Oh yeah, here was something. I don't know if you guys noticed this. So there's sort of this natural curriculum element to the paper because you only use the model's prediction as a pseudo label if it crosses this confidence threshold. That means at the beginning you're not doing much pseudo labeling, you're only doing consistency regularization, but as you get more and more confident, every now and then these pseudo labels start popping up, and it's probably the case that the easiest images to label become the most confident the most quickly. And what that means is that you can start incorporating that information into your model quickly, and then it'll sort of automatically be the case that harder and harder images will be delayed more and more. And so, so that means like there may be this, like it may be that this thresholding idea is like actually really important, and that it's because it's giving you curriculum for free. I don't know, but it is interesting. I mean, they did do an ablation on that. Let's see if we can find it. It's right here. So this was the confidence threshold. Depending on where you set the confidence threshold, you get different error rates. So I don't know if your confidence threshold is too low, then I guess you don't get very good error rates. If your confidence threshold is higher, then you get better error rates. But interestingly enough, like, I mean, it doesn't matter that much. It's just like 1 percentage point here. Brandon says, most people have to figure out stuff on their own and then get some guidance in order to fine tune their understanding. Yeah, I hear what you're saying. Okay, cool. Well, that's all I wanted to say about this paper. Hopefully you had fun reading it. I sure did. I think it's so interesting to read about all this semi-supervised and structured learning stuff. Self-supervised stuff. Like I said, I feel like it's important for us to spend time on this because I feel like this is the future. I think you'll see more and more stuff like this. So for those of you that are interested in pursuing deep learning or doing it in your own research, I hope that you're really drinking deeply as we go through this stuff. All right, let's call it there. Hope everyone has a great day, and we will see you on Friday. Hopefully my camera will be working by then.